Hello and welcome back, everybody. Moving on to the second subsection of line integrals. We're talking about vectorial line integrals today, and as well as the fundamental theorem of line integrals, but really this fundamental theorem only applies to vectorial line integrals. And it even actually only applies to a subset of those vectorial line integrals. So quite a few specifications as to when we can actually apply the fundamental theorem. But in terms of the vectorial line integrals, let's just have a quick reminder. We did technically define these in the last video, but we didn't use them at all. The definition of a vectorial line integral is we're going to have a vector field that'll map n-dimensional space to itself, and a path which will map an interval t-min to t-max out to Rn. Then the vectorial line integral is defined by, well, it's defined over a curve, technically, and then this vector f dot product ds, s is also a vector, so it's the dot product of the vector field with the tangent vector to the curve. And what does that look like? Computationally, it's t-min up to t-max, and then we take the vector field evaluated on gamma, and then that's a dot product with gamma prime of t dt. And in fact, these are going to generally be easier to compute than in the prior setting, because in the prior setting we had to take a magnitude of this gamma prime, right? And that magnitude got in the way of a lot of integration techniques because you'd have a square root of some squares. But now that we're just doing the dot product with the derivative, we're going to avoid those square roots. So integration actually gets easier in the vector line integral section, and especially it gets easier with the fundamental theorem of line integrals, which we'll see. So then very quickly, I think we should motivate these integrals. Why do we actually care when they're getting used? We're caring about them mostly from the context of physics, and as a subset of physics, something called field theory. And the first time I talked about field theory was way back when we discovered divergence and curl. Divergence and curl were kind of subsets of field theory because we had these Maxwell's equations, right? We had like the curl of an electric field was always equal to 0, or the divergence of the magnetic field was always equal to 0, and some of the other Maxwell's equations. Those are all subsets of field theory, and of course that was the first time we encountered vector fields, and what do you know, we've got vector fields here. But what about field theory and physics is line integrals actually trying to compute for us? Well, we'd like to think about our vector field f kind of actually as a force field. So here, force fields mentioned, science fiction, those are fields that like push different objects away, different trajectories away. That's not what these force fields are referring to. They're referring to, for example, gravity. The gravitational field is a field of forces, right? Gravity is constantly exerting a force on all of us, and it's represented as a field in physics field theory. So any sort of field that will apply a force on the objects which exist within it can be considered a force field, and that's really what these objects, vector fields and vectorial line integrals often are. What does the line integral compute? Well, I've got it labeled at the bottom here. We see a W equals F dot D. This is really the work as a physical quantity is equal to a force, and then that force is applied over a D displacement. So the fact that the force gets applied over a displacement to compute a work, that dot right in between the force and the displacement, that dot is playing the same role as the dot product in our line integral. So we really think about each quantity inside of the line integral as an infinitesimal force applied over an infinitesimal displacement. The infinitesimal displacement, of course, deriving straight out of gamma prime of t dt, because that's just d gamma of t, and we already saw in the last video that really this is it's the infinitely small displacement along the path, right? You can break the path into infinitely many infinitely small vectors. That's what d gamma really is, and so that d gamma is what's getting multiplied by our force field f. So really we're just computing the total work. You can imagine it's the total work over this curve subject to that force field, and it gets computed as a line integral. I've got the image here where we can make things a little bit clearer. I've brought the actual curve, which here I've just embedded as a circle centered at the origin. So here's the curve over which I would like to compute total work. So if I want to compute total work applied by the ambient, we'll call it a vector or a force field, which we've also drawn as the background, all of those little vectors in the background, compute the total work applied by the ambient force field as the line integral. And if we're caring specifically about how this is a specific location that it kind of zoomed in on, that specific location, if we care about really the work that's being done by the force field, we need the dot product of vectors to determine how much the force aligns with our trajectory. Right, because in the event that the force and the trajectory are orthogonal to one another, in fact, it's not the vector field that's doing any work, it's something else. Something else is causing the work to be performed, and that something else may just be a force applied by the object itself, right? If I push orthogonal to the direction of gravity, it would be like me running horizontally. Gravity's not doing any work on me, I'm doing the work myself. On the other hand, if I fall down a slide, then gravity is doing some of the work, which is causing my motion. And in some sense, I don't have to do the work myself to fall down a slide. So if we care about the work that the force field is actually applying, that's why we need that dot product. That's why I provided this little theta here to describe the angle. Recall that the dot product kind of refers to the angle between two vectors, up to a cosine. So we're really testing the parallelness of the force field, the force that's applied to my particle or my trajectory, as well as the trajectory itself, to compute that total work, if we only care about the work performed by the force field. But of course, this is just one location, and then we add that up at every single location here. We're always computing these dot products. So here, for example, it turns out you would have to apply quite a bit of force yourself, because your trajectory is pointing exactly in the opposite direction of the force field that's being applied. And so you would actually talk about negative work occurring in that situation. And of course, the dot product of those two vectors is a negative number. So added up all the way around that curve, you're going to get the total work applied by the field. So let's go ahead and compute one of these examples. So example of computing total work performed by a force field. Below, I've presented my force field. Here's capital F, the output being y minus z, x minus y, and z minus x, as well as maybe a trajectory given here, t squared, and t cubed. So if we want to actually compute this, we're just going to compute it right along by its definition. We're looking at the minimum time and the maximum time. Those are going to be the bounds on the integral, as well as the dot product, right? The dot product of the force field evaluated on the curve with the derivative of the curve itself. So let's go ahead and compute the derivative of the curve really quick. We're going to get 1, 2t, and 3t squared here. That's what you can see down there. I'm evaluating the force field on gamma, and the first input in gamma is t, second input in gamma is t squared, and the third input in gamma is t cubed. So those are my three entries to my force field. And when I actually evaluate those entries, t in place for x, as well as t squared in place for y, and t cubed in place for z, we recover the integral, which is the dot product of the vector t squared minus t cubed, t minus t squared, t cubed minus t against 1, 2t, and 3t squared. And for dot products, we're just going to look straight across and multiply each of these and then add everything together. So there's my first two multiplied, my second two multiplied, my third two multiplied, all added together. Gone through some work to simplify those, but I believe you could do it. Simplifies to 3t to the fifth plus 6t cubed plus 3t squared. Now you can start to see, wow, what a simpler integral we have here versus scalar valued integrals. Much simpler than scalar line integrals, because we have no square root. So most students really like the vectorial line integrals better because we're missing that square root, which causes so many problems with trig sub and other techniques. So we're just going to find the antiderivative, pretty easy. T to the 6 over 6, t to the 4th over 4, t cubed over 3, and evaluate at 0 and 1. Simplify. Turns out you get a little lucky here. Get the value of 0. That's not really to be expected. That was just what happened in this case. But you shouldn't necessarily expect a value of 0 out of line integrals. That's just what happened to occur here as the total work performed over the trajectory. We are going to move forward now to the fundamental theorem of line integrals, and even though that last line integral really was pretty easy to compute, using the fundamental theorem it gets even easier to compute. Really quite a bit easier to compute. What does this fundamental theorem of line integrals actually look like? Well, it basically says, hey, if I'm going to take a vectorial line integral over the gradient of a function, taking the vectorial line integral over the gradient of a scalar field. And recall, gradients are vector valued themselves, right? So the gradient is a vector, so that's why this is a vectorial line integral, because that gradient is a vector. But the gradient has some scalar field associated to it, and that scalar field being f by itself. what you can do if you take the vectorial line integral of a gradient field is you can just evaluate the scalar field on the endpoints of the curve. It's equal to evaluating the scalar field and this is the scalar field which produced the gradient field. It's not any scalar field, of course. Scalar field which produced the gradient field on the endpoints of the curve. And of course, we know from the generalized Stokes theorem, these curves always do need to be oriented, so we should be a little careful. It's always the true ending point of the curve minus the true starting point of the curve. Right? So it's always, think about this as the f of the curve's end point minus f of the curve's starting point because of orientation. But yeah, that gets pretty easy. It means, hey, as long as we can recognize the vector field as the gradient of another field, our life gets very easy. So I'll just mention that here. As long as we can recognize the vector field of a vectorial line integral as the gradient of a scalar field. Now, not all vector fields will be the gradient of a scalar field, but if it is, our life gets easy. So if we can make that recognition, our life gets easy. And of course, why is this called the fundamental theorem? Because, well, you can think about that gradient as the derivative of the scalar field. And so what do we see? We see that the integral of the derivative is equal to the antiderivative, i.e. getting rid of the gradient evaluated at the endpoints. It's exactly the fundamental theorem of regular calculus. But on the plus side, I do like to show in the proof that this is actually a special case of the generalized Stokes theorem instead. So here we're going to start with the differential zero form f composed with gamma, which is just going to map a one-dimensional space to a one-dimensional space. It's a one-dimensional function. And let's go ahead and compute the exterior derivative of that differential zero form. Well, exterior derivative, of course, I need to pull d to the inside, look at the variable I have. That's going to be partial t, but then I'm going to pick up the differential in that variable. If I act partial t on f of gamma, the chain rule is just going to give me the derivative of f. Now it's a total derivative, right? Multivariable total derivative, because f was potentially a multivariable function, times the partial derivative of gamma, still against the differential of time. But what do we know about a total derivative acting on a vector that can be reinterpreted, in fact, as the gradient dot product that vector? And so that's where the dot product is actually showing up out of this exterior derivative. It just ends up being the gradient dot the derivative of gamma. Okay, so then if that's the case, what does this line integral mean? The line integral over c of the gradient dot gamma, that's the term that I just brought up. What do we actually have here? We actually have the integral over a domain omega of that, which was the exterior derivative of f of gamma. But the generalized Stokes theorem says, hey, I can just evaluate now on the boundary of omega and get rid of the exterior derivative. Well, what would the boundary of my curve be? The boundary of a curve is just its endpoints. Boundary of a curve is just its endpoints. So the Stokes theorem says, f of gamma evaluated on the endpoints, c start, and then c end, we just get f of c end minus f of c start. That is the generalized Stokes theorem applied here. It's kind of cool. Think about it that way. You can also just prove it using calculus 1, actually, and I guess the chain rule of multidimensional functions. But yeah, it's a little funner to see it as generalized Stokes theorem. Okay, let's talk about the corollary. The corollary I have here is really the practical version of this fundamental theorem of line integrals, because it's not going to be so clear. Nobody presents you with a vector field and says, by the way, that vector field is actually the gradient of something else. It's kind of our job to find that out about the vector field ourselves, and so that's where this corollary shows up. So in terms of the corollary, let's say we're just presented with a vectorial line integral, where we've got some vector field, f, and we've got some curve c. And let's say we don't even have gamma yet. We don't really necessarily need to know gamma. What we do need to know is whether this is, I'll say, gradient of f for some f, right? Can we tell if that vector field is the gradient of some other function? Well, thanks to differential forms, we can, because recall the gradient of a function is actually the exterior derivative of that function, technically transposed, but we're not going to worry about the transpose. The gradient is really the same as the exterior derivative. We can tell when a scalar field has already had an exterior derivative taken of it by just computing a second, right? Compute one more exterior derivative. And Poincaré's lemma says it has to be 0, right? D squared of capital F would have to be 0, but of course that means lowercase f, which is the first copy of D capital F, just one extra exterior derivative. That should be 0. In other words, is it closed? If it's closed, it has a primitive, and the primitive of a gradient would just be the scalar field which produced the gradient. Anyway, so the corollary really is stated is we're going to check, interpreting the corollary another way, check if this is a closed differential one form. If yes, the fundamental theorem applies. And so find a primitive and evaluate on the endpoints. Because that's all the fundamental theorem is telling us to do, is compute the primitive function and then evaluate on the endpoints. That's the good corollary here. I've got really a little tiny extra corollary as well. In the event that C is actually a closed curve or a loop, I'm thinking of something that looks like, I don't really care where it goes, but as long as it starts and ends in the same location, and my vector field is a closed differential form, then the line integral, the vectorial line integral, will have to be equal to 0 because capital F of C start is equal to capital F of C end, because C start and C end are the exact same spot. And so if I subtract them from each other, of course, I'm going to recover 0 out of everything else. So that makes my life a little extra easy when I have closed loops and I guess closed differential forms. Closed unclosed, you get 0. I have a remark here that's talking about the kind of the physics names for all of the objects here. We talked right away about how this is really used to compute the total work performed on a particle moving along a trajectory. And so this is really strongly used in physics. They have a very slightly different name for every single function we see here. So in physics, you're going to see one of these closed differential one forms, as in the vector fields for which the fundamental theorem applies. Those vector fields in physics and even a lot of applied math are going to be called conservative. So you'll look for something called a conservative vector field if you're in physics literature. That just means we have a closed differential one form. df is equal to 0. And when we take the primitive of one of these closed differential one forms, or equivalent like the antiderivative, right, that's going to be called the potential function. So why do we call it a potential function? It's because these functions create potential energies, and then they apply forces down their gradient. So that's why the physics literature calls them potential functions. It turns out whenever you find one of these, they're representative of a potential energy of some form. So with that said, if we have gradient notation, we can think about the gradient of f as a conservative vector field, and then f, the antiderivative of the gradient, is the respective potential function. And then if we want to directly translate the statement of the fundamental theorem of line integrals, we end up with kind of the physics interpretation. The line integral of a path through a conservative vector field is equal to the potential function difference of the endpoints of that path. In other words, how much work is done by gravity if I roll a ball down the hill? Think about potential energies. Gravitational potential energy only cares about height, cares about your starting point and your ending point. It does not care about the direction the ball rolled down the hill. It's the easiest way to think about it in the physics setting. I've also got a comment on Maxwell's equations here. What is it saying about Maxwell's equations? Recall that the curl of the electric field is 0, and so electric fields happen to be conservative vector fields, and so the fundamental theorem of line integrals is basically saying that voltage, right, the potential of an electric field is actually a well-defined object. You can define a potential for an electric field. So that's kind of a nice way to think about it as well. So now that we know about the fundamental theorem of line integrals, I'm just going to go through 3 examples, the first 2 where we will be able to apply it, and then the final where we'll see that we don't have a conservative vector field. All right, so in this first one, suppose I'm given the following vector field, f, which is defined by cosine y, negative x sine y plus sine z, and y cosine z is my 3 outputs of the vector field, as well as a path given by cosine inverse, root 1 minus t squared, and sine inverse of t, with the t bounds negative 1 to 1. Let's see if we can compute the line integral of this vector field f along the curve c, where c is defined by the output of the path gamma. Well, to try to apply the fundamental theorem of line integrals, we need to check if that is conservative or equivalently closed. So our first step is to determine if this is closed or conservative, the same word, right? I want you to get used to both words in case you end up in a physics class next. There are two ways to do it, specifically when we're in R3, because when you're in R3, we have this notion of the curl, which really will produce, d squared of the potential function. So d squared, potential function we would hope would be 0, so we're asking the question, is the curl equal to 0? It works in R3 to determine if you have a conservative vector field, or we could go through the work and actually convert f into a differential one form and then check and see if it's a closed differential one form. In other words, is the exterior of f equal to 0? I'm always going to do it that way because I am a mathematician and I would like to do this in any number of dimensions if somebody asks me to, and when I do it in any number of dimensions, this is the way I'm going to have to do it. So what's going to happen here is I take my vector field, which recall was defined by cosine y, negative x sine y plus sine z, and y cosine z. I'm going to associate to that vector field the basis of differentials, and that will send me to a differential one form, right? Because I'm taking cosine y associated dx, I'm taking x sine y sine z associated dy, and I'm taking y cosine z associated to dz, and that's going to give me my differential one form. Then I can compute the exterior derivative of this differential one form and see what I get. So recalling how to do that, I'm going to take d on cosine and then pay the price of a wedge. I'm going to take d on negative x sine y plus sine z, pay the price of a wedge, and take d on y cosine z and pay the price of a wedge. When I compute each of those exterior derivatives on the inside of the scalars, I'll end up with a sine y dy. I'll end up with sine y dx minus x cosine y dy. That's the product rule in that term. And I'll have a cosine z dz. And I'll also have a cosine z dy and a y sine z dz, which is the product rule on that term. Then applying dx over, applying dy over, dy over, and dy over, and applying dz over and dz over, well, we see that we've got two copies of dz here, so that term's going to cancel, two copies of dy here, so that term's going to cancel, and I'm left with a couple copies of dy wedge dx's and a couple copies of dy wedge dz's, and it turns out if I pay the price of exchanging their order, right, flipping those two around, I'll get a plus here, and flipping these two around, I'll get a minus here. Turns out everything will cancel, and I get 0. Or in other words, yes, my original vector field was a closed differential one form. So there you go. I've checked if it's a closed differential one form. Equivalently, it is a conservative vector field. That means a primitive exists. I can apply the fundamental theorem, and I'm just going to compute the antiderivative, or the primitive of this function on the endpoints of the curve. So now I need to actually find the primitive, and if we recall, thanks to this proposition 4.3.7 in the earlier chapter, we can compute a primitive using the following formula. This formula works for all closed differential one forms, I guess in this case a three-dimensional version. But what I do is I evaluate my vector field on tx, ty, tz. I take the dot product with x, y, and z, and then dt, and I integrate that from 0 to 1. What am I going to get here? Well, I'm going to get a cosine ty, because that's the x entry evaluated on ty. I'm going to get negative tx sine ty plus sine tz. That's the y entry evaluated on tx, ty, dz. And then I'm going to get ty cosine tz. That's going to be the z entry evaluated on ty and tz. Then I perform the dot product, and that's going to leave me with, I guess, an x cosine ty. It's going to leave me with y times negative tx sine ty, as well as a y sine tz. And I'll have a z times ty cosine tz. At this stage, I should probably simplify a little, and I certainly can. I can pull the coefficients that I'm not integrating, an x, an xy, a y, and a yz, out, and then let's think about how I'm going to integrate each of these. That's going to be a u sub with u equals ty. That's going to be an integration by parts, where I'm taking a derivative of t and then an integral of sine ty. This is going to be a u sub with u equals tz, and then I'll have another integration by parts with a t is the one I take a derivative of, and cosine tz is the one I integrate. So we see that here. Here's my u sub on cosine. Of course, the antiderivative of cosine is sine. And then my integration by parts, where I take a derivative of t and then an integral of sine. So the integral of sine, of course, being cosine and cosine. And I'll do another u sub here. The antiderivative of sine is negative cosine. And then I'll do another integration by parts. So I'll have the antiderivative of cosine, which will be a sine here and a sine here. So yes, a lot of work, but hopefully that starts coming back to everybody, how to actually integrate functions. And then we're going to apply each of these on the bounds, right? 0 and 1, 0 and 1, 0 and 1, 0 and 1. And we will have to finish out these last two integrals, but they're just going to be one more copy of an integral of cosine and an integral of sine using a u sub. So here's my integral of cosine as negative sine. Here's my integral of sine as cosine. Then when I evaluate the bounds here on 0 and 1 and 0 and 1 again, and simplify everything, we call sine 0 0, sine 0 0. Here I have a 0 multiplying cosine 0, sine 0 0. And then very much at the bottom, I have a x over y sine y canceling with an x over y sine y. I have a y over z cosine z canceling with y over z cosine z. I have a y over z cosine 0 canceling with a y over z cosine 0. And I'm left with simply x cosine y plus y cosine z. So this is my primitive function. Or if we like to be physicists, my potential function. And the fundamental theorem of calculus tells me once I have a primitive or a potential function, all I have to do is evaluate on the endpoints, right? My primitive evaluated on the endpoint, primitive evaluated on the starting point. Now, what was my curve? Let's recall the curve really quick. The curve was equal to cosine inverse t root 1 minus t squared and sine inverse t over the interval -1 to 1. And so I'm just going to plug in this 1 into each case of t for my upper endpoint, and I'm going to plug the -1 in for each of these for t for my lower endpoint. And if we don't recall, cosine inverse of 1 is 0, sine inverse of 1 is pi over 2, and then the square root's easy enough to compute at 0 in the first case. And then cosine inverse -1 is pi, sine inverse -1 is negative pi over 2, and then once again the square root term's easy enough to compute as well. And so we're just finding our primitive evaluated on these terms. What was my primitive? It's right up here at the top. X cosine y plus y sine z evaluated at 0, 0, pi over 2. That ends up actually giving me a 0. And then evaluated at pi, 0, negative pi over 2. That gives me pi times cosine 0 plus 0 times sine. 0 times sine cancels. I just have pi times cosine 0. That's pi times 1 with a negative sign. I get negative pi out of this. Now, you may be tempted to say that this was not an easy line integral to compute because of all of that work required, testing whether or not I had a closed differential form, finding its primitive, etc., etc. I do encourage you to attempt to compute the line integral by direct means alone and see which one you think is easier, because if we go back to the original definition of these functions, can you imagine taking a derivative of this and then taking the dot product of that derivative against this, where this is actually evaluated on gamma? It's going to look really ugly if you evaluate that on gamma and then take a dot product and then start trying to integrate. I promise you it's quite bad. So it may seem like this was a lot of work anyway, but it's substantially less work than we would have had to do before. So I got another example of the fundamental theorem of line integrals in action. Here we have a two-dimensional vector field. So we've reduced our dimension a little bit, calling it G. The first output is 3x squared y plus 2xy squared minus y cubed. Second output is x cubed plus 2x squared y minus 3xy squared. And then we're going to evaluate this as a line integral against the path gamma given by sine 4t cosine of 3t over the bounds 0 to 2 pi. Now I have plotted this below. And there you can see the beautiful path embedded in the vector field. Notice that path is closed. So very importantly, if we note that it's closed, because of that corollary, the line integral over a closed path, as long as the vector field is conservative, has to be 0. So we're really going to cross our fingers that this vector field is conservative, because if it is the case, then the line integral over that vector field will just be 0. We know that because it's a closed curve. All right, so how are we going to tell if this is a conservative vector field? Well, we're just going to go ahead and compute the exterior derivative, right? So we're going to compute G into a differential one form, compute its exterior derivative, and check if the result is 0. So there's my output of G, and once again, I'm associate dx and dy as the basis vectors of that. So here's my dx term, and then here's my dy term, and I'm going to compute an exterior derivative. When I compute the exterior derivative, there's the exterior derivative on the first scalar term, wedge dx, and then the exterior derivative on the second scalar term, wedge dy. And then when I compute the exterior derivatives of each term here, I will get using the product rule, 6xy dx plus 3x squared dy. Then another product rule, negative 2y squared dx plus 4xy dy. And then just the derivative of y cubed, negative 3y squared dy. That's all going to be wedged against dx. Then the second term, I'll have the derivative of x cubed, which is 3x squared dx, then a product rule, 4xy dx plus 2x squared dy, and then another product rule, 3y squared dx plus 6xy dy. All of that was wedged against dy. But notice over here, I have a dx wedge, which means that dx is going to go away, that dx is going to go away. And over here, I have a dy wedge, so that dy is going to go away, that dy is going to go away. And I'm just really going to be left with 3x squared plus 4xy minus 3y squared against dy dx, right? 3x squared, 4xy, 3y squared against dy dx. And I'll be left with a 3x squared, 4xy, 3y squared against dx dy, so 3x squared, 4xy, and 3y squared against dx dy. If I decide to combine everything together, I have, what do I have here? 3x squared. If I swap that around, it makes it negative, canceling with this 3x squared. They go away. Here I've got a 4xy, dx dy. That's going to end up canceling with the 4xy, dy dx, so those are gone. And even though I didn't write it below, I have a 3y squared, dx dy, and then 3 y squared dy dx. Those are going to cancel. And so the output here is just 0, meaning I have a closed differential one form, everything I wanted, meaning now a primitive would exist, but I don't really need to compute it because since the curve is closed, right, we mentioned that the curve was closed, meaning that this line integral has to be equal to 0. How could I tell the curve was closed without actually plotting it? Let's just test the curve on the endpoints. So testing the curve on 0 and on 2 pi, gamma at 0 looks like sine of 0, cosine of 0. That's going to be the point 0, 1. And then gamma on 2 pi will be sine of 8 pi, cosine of 6 pi. But of course, 8 is a multiple of 2, meaning that's just actually sine of 0, so that's still equal to 0. And 6 is a multiple of 2 as well, so that's the cosine of 0, also 1, because our starting point and ending points are the same. That's what's important. Starting and ending points are the same. And so since the starting points and the ending points are the same, everything cancels when you compute the fundamental theorem of the line integrals. One final example, and this is going to be an example where we can't actually use the fundamental theorem of line integrals because our vector field won't be conservative. We have the vector field x plus y and x minus y, as well as the path 1 plus 2 cos t, negative 1 plus 3 sine t. And I've gone ahead and plotted it here. We do, in fact, have a closed curve again, right, because our endpoints are 0 and 2 pi, where if I plug in a 0, I get, 1 plus 2, so I get 3 as the first output, and negative 1 plus 0, I get negative 1 as the second output, or if I plug in 2 pi, I get something similar, where I'll still get 3 and negative 1. So we do have a closed curve. It turns out to be an ellipse in this case. We can almost actually see that this is a non-conservative vector field because recall conservative vector fields have 0 rotation. Right? The kind of the Helmholtz decomposition would tell us that the rotation in a conservative vector field needs to be 0. Here we can definitely see some fairly non-trivial rotation everywhere. But let's say we didn't know that. Let's say we didn't know that we could graph this and see some non-trivial rotation and just have to find out whether or not this is or is not a conservative vector field. Let's just do that by converting h into a differential form and finding its exterior derivative. So there's h. I'm going to associate dx to the first entry, dy to the second entry. So my first term is x minus y dx, and then x plus y dy, and I'm going to compute an exterior derivative. So that's actually just d on x minus y wedge dx, and then d on x plus y wedge dy. What do I get? Well, dx minus dy wedge dx, dx plus dy wedge dy. Of course, if I'm distributing dy to both terms, it cancels with dy. If I distribute dx to both terms, it cancels with dx. What I'm left with is actually 2 copies of dx wedge dy. And so when I have 2 copies, of course, 2 copies of dx wedge dy is not equal to 0, meaning this is not a conservative vector field, meaning I cannot apply my fundamental theorem of line integrals. So no fundamental theorem of line integrals. What I can do instead of computing the fundamental theorem of line integrals, is let's just compute the line integral. We hopefully remember how to do that just by definition, right? If you can't use the fundamental theorem, just use the definition. Just use the definition of a vectorial line integral. And for that, we're going to need to evaluate our vector field on gamma, and we'll need gamma prime. Let's recall what gamma looked like here. Gamma of t was 1 plus 2 cosine t, and it was negative 1 plus 3 sine t. So I can compute that derivative pretty easily. It's going to be, I guess, negative 2 sine t and 3 cosine t. Okay, so I'm going to use that derivative right here that I just computed. I'm going to use the first output of gamma as the input to h, and then the second output of gamma as the input to h. And if we recall, h was x minus y and x plus y. So we're just going to use 1 plus 2 cos t for both cases of x, and negative 1 plus 3 sine t for both cases of y. And then we just simplify each of those. I get 2 plus 2 cos t minus 3 sine t, and 2 cos t plus 3 sine t. We take the dot product with our gamma prime. And that's going to give me a lot of terms because I'm just going to have to distribute negative 2 sine t to everything here. And I'll distribute 3 cosine t to everything here. And simplify, well, when we simplify, we get 4 sine t plus 5 sine t, cosine t plus 6. Thankfully, sine squared plus cosine squared. Don't forget our Pythagorean identity. That's equal to 1. So we really just get 6 times the integral of 1 there. We get an integral of sine times cosine and an integral of sine. Of course, the integral of sine is just negative cosine, but we already have a negative up front. Here I'm using a u substitution. What's my u substitution going to be? I'm going to let u equal sine of t, so then du can be cosine of t dt, and that's going to let me get sine squared over 2 as the integral there. And of course, the integral of 1 is just t. So now if I evaluate at the bounds, we have
plugging in 2 pi, I get a cosine of 2 pi, plugging in 0, cosine 0, plugging in 2 pi, sine squared of 2 pi, plugging in 0, sine squared of 0, and 6t, plugging in 2 pi, 6t, plugging in 0. Simplify everything. Turns out those are canceling. We get a bunch of sines equal to 0. We just get 12 pi. 12 pi over here as the final line integral in this particular case, even with a closed curve, right? So 12 pi is not equal to 0. This is showing the closed curve will have non-trivial work performed on it when the vector field causes rotation. This would make sense because walking around the closed curve, you're going to have rotation of your own. And of course, this rotation is going to align pretty closely with the rotation of the vector field below you sometimes, and that's going to give you some positive work that's been performed. It's only in the case when no work would be performed that, of course, doing a closed curve, you're going to have equal rotation in every direction, so everything's going to cancel out and you get 0. So just want to throw that out as one case. You do have to check if your vector field's conservative or closed before using the fundamental theorem, and especially that can give you cases where the vectorial line integral over a closed loop may not be 0 if you don't have a conservative vector field. We're going to stop there. It's been a good one. I hope it was a lot of fun. I was certainly having fun myself. See you in the next one. We'll talk about general Euclidean and dimensional integrals. So first time we're really doing higher dimensional integration. See you then. Bye.